So far in the lectures that you have gone through, we have basically discussed different ways in which you can design a digital circuit. But today in this lecture we shall be discussing slightly different issue related to digital circuits, namely once you have designed a digital circuit, it can be a circuit designed using gates on a breadboard, or it can also be a VLSI chip. How to test it? Because during the process of manufacturing or fabrication or prototyping, there can be so many different kind of errors that can creep in. So, a very important step in the entire design cycle is how to test the manufactured hardware. So, the topic of today's lecture is testing of digital circuits. Okay. So, let us first try to motivate ourselves and understand why we need testing. Okay. So, I have just now said that during the process of manufacturing, so when you say manufacturing, it can be manufacturing of a chip, manufacturing of a circuit on a breadboard using available chips, you interconnect them using wires. It can be at different levels, it can be printed circuit boards, many chips which are soldered together. Okay. So, once you have such a manufactured hardware, there can be various kind of errors which can come into the picture. Now, here I have highlighted 3 different kind of errors, but there can be other kind of errors as well. First is that, well, in the design process itself, let us say there were some errors. There are some errors during the design process. So, when you are designing the circuit, because of a human error or maybe the specification was not correct, there has been some problem there. Or normally we use some software tools for design and synthesis. These are called computer aided design or CAD tools. There can be some errors in the tools itself, because the tools are huge software, and testing a huge software is an enormous task. There can always be some errors that are sitting inside those tools themselves. Okay. So, there can be some errors or bugs in those tools, and finally, during the fabrication or packaging there can be some faults. For example, when you are connecting 2 points using a wire, there can be a loose connection for example, or there can be a short circuit, this kind of errors. So, because of such error occurrences, it is necessary to test each and every chip or manufactured device before they can be used. If you talk about the modern day VLSI chips, there are of the order of billions of transistors inside them. So, you can understand how complex the circuits are, and chances of faults creeping in such a very complex VLSI chip is also pretty high. Okay? Because of that, the problem of testing is important. Now, the basic objectives of testing. What is the basic objective that you are trying to meet? Okay? The point to note is that we use testing to determine the presence of faults if there are any. But there is a fallacy that someone thinks that, well, we do testing to guarantee that a circuit is fault free. But the problem or issue is that no amount of testing can give you this guarantee. Well, you can, for example, test and find out that your circuit is working perfectly at room temperature, but as soon as you increase the temperature by 5 degrees Celsius, your circuit fails. So, it is not possible to test the circuit against all possible environmental circumstances, temperature, humidity, there are so many parameters, right. Then the volt fluctuation in the supply voltage, there are so many issues. So, testing to guarantee that a circuit is fault free, this is a false statement. No amount of testing can give this guarantee. But however, what we do using testing, we can increase our confidence, this should be R. we can increase our confidence in the correct working of the circuit. That is why we use testing. And along with testing, we use another term called verification. Let us briefly talk about what are the main differences between testing and verification. Verification talks about the design. We want to ascertain whether the design is correct or not the actual hardware. Design we can do on a piece of paper, say a function minimize using Carnot map, that is an example of a design. Okay. So, verification concentrates on the design and it can guarantee the correctness of a design. Okay. Now, in contrast, testing, as I just now mentioned, it tries to, it can never give a 100% guarantee. It tries to guarantee correctness of the manufactured hardware. It can be circuits, chips, anything. For verification, because we are talking of the design which possibly you have done on a piece of paper, this is performed only once before you start the actual manufacturing. Right. Now, in contrast, faults can occur in each and every device. Therefore, testing must be performed on every manufactured device. This is one important difference. Verification assures the quality of the design, that the design is free of any errors. Testing ensures quality of the devices, that the devices are probably free of errors. Well, again I am repeating, you can never give a 100% guarantee. Okay. And verification is typically carried out using mathematical techniques, formal methods, theorem proving, simulation, but these are the things we shall not be discussing here. But for testing, we normally use a two-step process. Given a circuit with some inputs and outputs, first we find out that what are the inputs we have to apply for testing, that is called test generation. Then for every circuit or chip, we have to actually apply those inputs and verify whether the output is coming correctly, that is called test application. Okay. Fine. Now, the question is when we can do testing. You see, when a chip is manufactured, let us say, talk about a chip because chip is the most basic of the devices that we use today in our design. So, when do you do the testing? So, the point to note is that testing can be carried out at various different levels. Well, when the chips are manufactured, we can do testing at the chip level. When several such chips are integrated on a printed circuit board, we can carry out testing at the board level. And when you build a more complex system, there can be several such printed circuit boards that make up a system. So, when several boards are assembled together, we can finally test at the system level. But the point to note is that as we move up the hierarchy, so as the system becomes more and more complex, the problem of testing becomes more difficult. Testing a single chip may be easier, but when I say I have a system which consists of 1000 chips and it is not working, testing that 1000 chip assembly is a real much more complex problem. Okay? This is something you have to understand. So, rule of thumb says that you need to detect a fault early if possible, which reduces the cost of testing. There is an empirical rule. Well, as you move from one level of hierarchy to another, chip level, board level, system level, it becomes 10 times more expensive to test the device when you go from chip to board or board to system. So, it is always good to test a circuit at the level of the chip as soon as they are manufactured. Okay. Now, talking about the faults, how many faults may be there when you are doing testing. There are some important points to note. You see, in a circuit, means the number of physical defects can be enormously large. Well, when you say physical defects, there can be a short circuit, there can be an open circuit. Say a transistor may not be working properly, the gain of the transistor may vary. Now, these are all, you can say, continuous parameters. The gain of a transistor can vary. So, how much, varying by how much, you cannot quantify. It can be 1.1 times, 1.15 times, 1.155 times. There are infinitely many possibilities. So, you really cannot count how many such physical failures are there. They can be quite enormous. So, how do you judge the quality of a test? Now, the accepted solution in the industry is that you use something called logical fault models, where you are abstracting physical defects. Like you are not thinking about the actual physical defects, like there is a short circuit, open circuit, there is a change in gain of a transistor. Rather, at a much higher level, you are abstracting the failures and thinking about faults occurring at some other level. Like for example, a gate, you assume that one of the inputs of the gate is permanently at 0. That is one kind of a fault model you can think of. Okay? This is just an example. So, the advantage is that if you assume such a fault model, then it is easy to count the total number of faults, and also you can analyze how good your testing process is. That means, how many of those faults are getting detected, how many faults are getting tested. Okay? Fine. There is one parameter we use to assess the quality of testing. This is called fault coverage. Fault coverage is determined by two parameters. Okay, here the implicit assumption is that we already have a fault model. So, we already have a mechanism using which you can count how many faults are there in the circuit. This is our inherent assumption. Okay? So, the denominator here says total number of faults, and numerator is, well, we are doing testing and how many of these faults we are able to test. The ratio of these two is defined as the fault coverage. Sometimes we multiply this factor by 100 and express this fault coverage as a percentage. So, it is essentially percentage of the total number of logical faults that can be tested using a given set of test vectors T. Suppose for a circuit I say that, well, these are the 10 test vectors I have to apply to test the circuit. So, these 10 test vectors, how many faults can be detected by them? This is something which is determined by this parameter called fault coverage. Okay. Now, why testing is considered difficult? Well, you consider a simple combinational circuit. Let us say I have a combinational circuit with certain number of inputs and there can be one or more outputs. Let us say there are n inputs. Well, I can say that, well, let us follow a simple process. Let us verify the truth table. That is the best possible testing we can do. We apply all possible inputs and see whether the truth table outputs are matching. So, at the inputs we have to apply 2 to the power n combinations. Now, let us think of practical circuits. The value of n can be pretty large. So, here I am showing values of 25, 50, 100, but practical circuits can have of the order of 1000 inputs as well. But if we just show here what is the value of 2 to the power n, you see 2 to the power 25 is about 33 into 10 to the power 6, 33 million. 2 to the power 50 is 1 into 10 to the power 15. 2 to the power 100 is 10 to the power 30. So, you see numbers have become becoming enormously large. You really cannot apply so many test vectors in practice. So, it is just out of the questions. So, you would be requiring years and centuries to complete your test. So, this is not possible. Okay? This is why we say testing is a difficult problem, not feasible as n increases. Well, we have talked about combination circuits, but if you consider sequential circuits, the problem becomes even more complex. Suppose there are n number of inputs and s number of flip flops or state variables. So, there can be 2 to the power n number of primary inputs and 2 to the power s number of states. So, the machine can be in 2 to the power n multiplied by 2 to the power s, that many possible states. The output will depend on so many combinations. So, the complexity becomes of the order of 2 to the power n plus s. So, the problem is even more complex as compared to a combinational circuit. Verifying the state table of a sequential circuit is also infeasible. So, we need some mechanism for handling this complexity. We shall see later that we talk about some method called design for testability, which gives us a practical and feasible solution with which we can address this issue. Okay. Now, let us briefly talk about the various processes or steps that we carry out during the testing of a circuit. Some of this we shall be discussing, well, one or two of this we shall not be discussing as part of this lecture series. The first point I have already mentioned, this is most important, that modeling of the faults. Fault modeling, here we abstract the physical defects as we mentioned earlier and we define a suitable logical fault model. And so, we shall see examples of this later. This simplifies the scope of test generation, because now you can count how many faults are there. Let us say for a circuit you say that I have 20 faults. So, let me try to generate a test set which can detect these 20 faults, but unless this number 20 was given to you, it would be very difficult for you to generate the test set. So, you are testing for what? That question would come in, right. So, after fault modeling, next natural step is test generation. So, you are given a circuit and of course, after fault modeling you have a set of faults. So, you have to generate a set of test vectors T that can detect these faults. This is called test generation. So, here we shall also be very briefly talk about test generation. Then comes fault simulation. Fault simulation says, well, we have a circuit, we have a set of fault and also a set of test vector. Fault simulation is a software that will analyze the circuit and tell you that how many of these faults are getting tested by this set of test vector. Fault simulation is a very useful tool, but however, in this lecture series we shall not be talking about fault simulation, but just remember fault simulation is also a useful step in testing. Then you have something called design for testability. Design for testability says, well, we talked about the thing that the problem of testing is quite difficult. Combination circuit is difficult, sequential circuit is even more difficult. So, design for testability or DFT in short, it consists of a set of design rules which if you follow during design, it will make a circuit easily testable. This is the basic idea. Okay? Well, of course, if you do this, there will be some additional overheads that will come in. We shall look at one of the techniques later. And finally, you have something called built-in self-test, where when you fabricate a chip, some testing hardware is also fabricated inside the chip itself. The chip can test itself. From outside, you need not have to do anything. The chip will tell you that I am good or I am bad. Okay? So, these are the different processes that we typically talk about during the process of testing. So, this is the overall picture. Here we have a circuit that you want to test. We apply some input patterns, you get some outputs, you know what is your expected output, that is called the golden response. You compare the output response against the golden response, and if they match, you say it is okay. If they do not match, you can say that your circuit is bad, it is not working. Okay? This is a very overall simplified schematic diagram. So, with this we come to the end of this lecture, where we have introduced you to the basic problem of testing. Now, over the you can say next few lectures, we shall be talking about the different steps that we talked about, the important steps, fault modeling to start with, that are required in the process of testing. Thank you.